morning. Okay, let's start because I'm using the Zoom, the personal version of Zoom. I have the time restriction. I only can record 40 minutes. So let's start and use the time. Okay, we continue with another example. During my explanation, if you have any question, please ask me, stop me and ask me, okay? So start with this example. We have several examples from last week. Okay. Here we have an arm OA of the classifying accelerometer, has a mass of 0.25 kilogram with center of mass at G. Here we have a mechanism includes several particles, several bodies, but the total mass center is located at here point G. So here this is the mass center. The adjusting screw and spring are preset to a force of 12 Newton here. So at point B, at this point, we use a spring to insert a 12 Newton force on this arm OA. At what acceleration A, so this is the acceleration A, would the electrical contact at A be on the verge of opening? Here at point A, the contact will be on the verge of opening. Motion is in the vertical plane of the figure. So the first point and the key point in this problem is that when contact at A is on the verge of opening, so here the normal force will be 0. So we can plot the free body diagram. If we plot the free body diagram, we will have two forces at point O, OX and OY. We will have the force exerted by this spring at point B and the normal force at point A. The normal force at this point, according to the problem description, it must be equal to 0. So now we can write the force equation in y direction. If you write the force equation in y direction, since our motion is in horizontal direction, so in vertical direction the acceleration is 0, so it's similar to the static problem. We can write the force equation in this direction. We will have OY minus this force, which is 12 Newton. So we assume that the upward direction is positive, okay? And also we have the weight of the system, which is exerted here at point G. So we will have mg, it must be equal to 0. We have the m, which has the mass of 0.25 kilogram, and g you can substitute and simplify, and finally we can conclude that the vertical component of the reaction force at point O is equal to 14.45. And now we can write the moment equation about the mass center. It must be equal to I alpha, because we are writing the moment equation about the mass center. In the right hand side we will have I alpha, but since this is a translational motion and there is no rotation, so the acceleration, angular acceleration, is equal to 0. So again, it's similar to the static problem. We can write the moment about point G. We know that NA is equal to 0. We will have the moment due to the OY, this force. We have the moment due to OX, and finally the moment due to this force B. Okay, the moment due to OY is equal to OY times by its arm, which is 30 millimeter or 0.03 meters. The arm for the force OX is equal to again 30 millimeter or 0.03 meter, and the arm for this force 12 Newton is 15 millimeter or 0.015. Okay, so we can write, and according to your assumption, you can consider negative or positive for the direction of the moments. For example, here We assume that the counterclockwise direction is positive, so the moment due to OX is positive, the moment due to OY is negative, and again the moment due to 12 Newton is negative. And this NA, the arm for NA is 90 millimeter, but since NA is equal to 0, so we can substitute instead of NA 0, and we can find that OX is equal to which quantity? Okay, so this is 20.25, which is the horizontal component of the reaction at point O. And the last point, we need to obtain the acceleration. We can write the force equation in x direction. If you write the force equation in x direction, we will have OX and A. OX is equal to 20.25 and NA is equal to 0. So the acceleration is equal to OX divided by M. And easily you can find the acceleration for this system. Okay, clear? No question? Okay. The next problem, we want to determine the magnitude P, this force, this is P. Okay, we want to obtain this force P and direction theta of the force. So we need also obtain the theta required to impart a rearward acceleration 5 meter per second square to the loaded wheelbarrow with no rotation from the position shown. The combined weight of the wheelbarrow and its load is 500 Newton with center of gravity at G. This is the mass center for the whole system. Compare the normal force at B. Here, this is point B. We have one normal force under acceleration with that for static equilibrium in the position shown. So neglect the friction and mass of the wheel. So here we should write first obtain the P and theta to find the P and theta to have a pure translational motion. So we need to obtain the moment equation about the mass center or any other point. It must be equal to 0. And then we can write the force equation in x direction with the acceleration A. And then we need to compare the normal reaction at point B for two different cases. One, when we have motion with the acceleration A, and second for the case when the system is in a static equilibrium condition. So first, let's plot the free body diagram and find the reaction force. The first case, we need to find the static equilibrium condition. In the static equilibrium condition, if you write the moment equation about A, about this point, this is the best option because you don't need to find the P and theta. In this case, you can easily write, we have one force here at point B times by its arm, which is 100 centimeter plus this 20 centimeter or 1.2. And the other one is the weight here at G. Again, the arm for G is 100 centimeter or 1 meter. If we assume that the counterclockwise direction is positive, so the moment due to the mass is equal to a negative value, and we can find the NB or the normal reaction at point B, which is equal to 416. So this is the static value when the system is under a static equilibrium condition. The second case is when the system is moving with acceleration A. In this case, you can write the force equation in x direction. When you write the force equation in x direction, we will have P times by cosine theta, the horizontal component of P, and it must be equal to the mass times by the acceleration. The acceleration is 5 and the mass is 500 divided by G, because we know the weight is 500, so the mass is weight divided by g. So here we can calculate that the the p times by cosine theta is equal to this value, 255.1. The second equation, we can write the force equation in y direction, again because the motion is in horizontal direction and there is no motion in vertical direction, so the equation in vertical direction must be equal to 0 because there is no acceleration in this direction. So the summation of the force in y direction is p times by sine theta. We have the NB here, we have this force, the normal force, and also we have the weight, which if we assume that the upward direction is positive, we will have a negative sign for mg. So this is the force equation in y direction. It must be equal to 0. So from the second equation, we can conclude that P sine theta is equal to 500 minus NB, which 500 is mg, or the weight of the system. And finally, we can write the moment equation about the mass center. Since there is no rotation and the motion is a pure translational motion, so in the right hand side, you can see we have 0 again. So the summation of the moment about g must be equal to 0. For force P, we will have P cosine theta, the vertical component, the horizontal component, and P sine theta, the vertical component, times by their arms. The weight is located on the mass center, so there is no moment due to the weight. And finally, we have this normal force at point B. So P cosine theta, or the horizontal component for the force P, must be multiplied by its arm, which is 60 minus 50, which is equal to 10 centimeter or 0.1. P sine theta, or the vertical component of P, multiplied by its arm, which is 100. Again, here you can see this is the arm for the P sine theta. And finally, the NB must be multiplied by its arm, which is 20 centimeter. The direction for P cosine theta is about G is counterclockwise. For NB, the moment due to the NB about mass center is again counterclockwise, but the moment due to P sine theta, or the vertical component about G, is in clockwise direction. So you can assume one direction for your positive direction and calculate the moment equation. It must be equal to 0. Now you can extract another equation for P, theta, and NB. So we will have 3 equations, one here, the second equation is here, and the third one is here. So we will have 3 equations with 3 unknowns, and you can obtain 3 unknowns, which are NB, theta, and P. If you substitute 1 and 2 into the third one, you can obtain that NB is equal to 215.6. So we will have P cosine theta from the first equation, P sine theta from the second equation, 500 minus NB. This is the second equation. And if you substitute here, you can find the tangent theta. If you divide P sine theta by P cosine theta, you can find the tangent theta, which is equal to 1.11. Now you can find theta and substitute and obtain P. So if P was equal to 381 and theta was equal to 47.98, or about 48 degree, this system will move in a horizontal direction, and the motion will be pure translational motion. And also you can compare this NB with the static value. So when you are moving with the acceleration a, which is 5 meters per second square, in the direction shown here, the force reaction at point B will be decreased by about 200, okay, 200 newtons. In the static one, the force reaction at B is 416, but in the dynamic one, when you are moving to the left direction with the acceleration of 5 meters per second square, the normal reaction is about 215. So you decrease the force by about 200 newtons. Okay, clear? Any question? Okay, thank you. Okay, we have another example. This is the last one. The loaded pickup truck, which weighs 3,600 pounds with mass center at G1. Here you can see. Let me change here. This is a G1. The mass center for this pickup is hauling the 1,800 pound trailer with mass center at G2. This is the mass center for the trailer. While going down a 10% grade, here you can see this is the grade, a 10% grade. You can easily find the theta or the angle of the grade. The driver applies his brakes and slows down from 60 miles per hour to 30 miles per hour in a distance of 360 foot. For this interval, compute the X and Y components of the force exerted on the trailer, each at D, by the truck. So we need to obtain the reactions, normal and horizontal reactions, of course, according to this coordinate system X and Y at point D, while this pickup is moving down with a deceleration that we should calculate this from this data, and also find the corresponding normal force under each pair of wheels at B and C. So this is B and C. We need to obtain the corresponding normal force or normal reactions. Neglect the rotational effect of the wheels. So here again, we can assume that we have only a pure rotational motion, pure translational motion, and there is no rotation because this system is moving in X direction, and we can neglect the rotational effect of the wheels. So first we need to obtain the acceleration for this system. To find the acceleration, we need this data. The velocity decreased from 60 to 30 miles per hour in a distance of 360 foot. So we can easily find the acceleration for this motion by assuming a constant acceleration. This is up to you. This is your assumption. I assume that the acceleration is constant, so we can easily use this formula. The final velocity squared minus the initial velocity squared is equal to 2 times by the acceleration times by the distance. So we can use V sub 2, which is 30 miles per hour. The initial velocity is 60 miles per hour. I should convert it into the foot per second. And finally, you can substitute and find the acceleration, which is minus 8.07 foot per second squared. This is the acceleration during this motion. Now we need to plot the free body diagram. This is the free body diagram for the trailer. If you plot the free body diagram at point C, we only have one normal reaction. At D, which is similar to a pin connection, we will have two reactions, one in X direction and the other one in Y direction. We call them dx and dy. Now we can find the theta, the angle for this grade, which is equal to the tangent inverse of 1 divided by 10. Now for the trailer, we can write the force equation in X direction. It must be equal to the acceleration AX, which we calculate this in the previous slide. And M2 is the mass for the trailer. So we are writing the force equation, the kinetic equations for only the trailer. So we plot the free body diagram, and in fact we detach the trailer from the pickup at point D, and instead of the forces, instead of the connection, we substitute the forces. Okay, so in X direction we will have the weight times by sine theta, the X component of the weight, which is this force. The X component is equal to weight times by sine theta minus dx, which dx is the X component at pin connection D, it must be equal to AX, which is weight divided by G. You know that in US system, US measure system, instead of 9.8 for G, we have 32.2. Of course, as I told you, we don't have any problem in this unit system, and all of the problems for you in the exam is in SI unit system. Okay, so don't worry about these values. So here we convert the weight into the mass, and it must multiply by AX, which is the acceleration calculated in the previous slide. So now we can calculate the dx, or the x component of the reaction at point D. The second equation that we can use to find the dy, we can write the moment equation about point C, about this point. If you write the force equation in y direction, we will have two unknowns. One is the normal reaction at point C, and the other one is the normal reaction at point D. So if you write the moment equation about C, you only have one unknown, and that's dy. And it must be equal to IC times by alpha plus MAD. You know, when you are writing the moment equation about any other points than the mass center, you will have another extra term here, which is MAD, mass times by the acceleration times by the distance between that point and the mass center. And IC alpha, which is the acceleration time, angular acceleration times by the mass moment of inertia. Here, because we don't have any rotational motion, this term is equal to 0, but we have m times by a times by d, and a is the acceleration calculated in previous slide. So you can write the moment equation about point C. When you write the moment equation about C, we have the moment due to dx, the moment due to dy, and this weight will have two components. The vertical component, or the y component, will pass through point C, doesn't have any moment, but the x component, which is mg times by sine theta, will have moment, and its arm is equal to 40 inch. Okay, so you can substitute here. We will have dy times by its arm. Dy, its arm is 50. Dx, its arm is equal to this length. Okay, we have this length, which is equal to 50 times by, here we have 20 dy. Yes, this is 24 when you are calculating the moment about point C. It must be, yes, this is 18 here. It's very busy here. I couldn't find this. This is 18. The arm for the dx is the distance between the dx and point C, which is 18 inch. So here we have 18. And finally, for this force, the x component of the weight, the arm is equal to 40. So you can substitute. It must be equal to the mass times by the acceleration. The mass is again this term, the weight divided by 32.2, the acceleration ax, which is calculated in the previous slide, and times by d, the distance, which is again this length, 40 inch. Now you can substitute and find dy, which is 277.2 pounds. And this is the dy. And now you can write the force equation in y direction. If you write the force equation in y direction, we only have one unknown, which is the normal reaction at point C. And also in the right hand side, we have 0 because this system is moving in x direction. So in perpendicular direction or in y direction, there is no motion, and so there is no acceleration, and it's equal to 0. From this equation, we can conclude that NC is equal to the y component of the weight minus dy, and it's equal to 1,513.86 pounds. And this is the normal reaction at point C. So this is the first part of the problem. And in the next part, we need to obtain the reactions at point B. Okay, any questions so far? Is it clear? This is a translational motion, and in all of the cases you see that there is no angular acceleration, and in all of the moment equation you can see in the right hand side we consider that the angular acceleration is equal to 0. Okay, so let's move to the second part of the problem. In the second part we consider only the car as a system. Instead of this pin D we assume and we substitute the reactions dx and dy. We calculate dx and dy from the trailer free body diagram, but here you can see we consider the opposite direction for dx and dy because these are the reactions. So you can substitute dx and dy, and for at point B we will have two reactions. At point A again we have two reactions, because this is a pickup and we can assume that all of the wheels are drivers. So at each wheel we have, in addition to the normal reaction, we have one horizontal component. Okay, now we need to obtain the reactions at point B. So for this purpose, we can write the moment equation about point A, about this point. When you write the moment equation about this point, the reactions at point A will pass through this point, so they don't have any moment. And you know that again, you're writing the moment about point A, which is not the mass center. So in the right hand side, we will have IA alpha plus M1 AD, which again, the alpha, this term is equal to 0. And we have M1, which is the mass of the pickup or mass of the car. We have the acceleration, which is calculated, and the D, which is the distance between the mass center and the point A, which is equal to, I think it's equal to 24. Yes, this distance. Okay. Okay, because the acceleration here, there is another point you should consider in your calculation. The distance between the mass center, this point, and point A, if you want to find the horizontal distance, is equal to 58. Okay, let me move this slide. Okay, it's better. Here, if you want to find the distance between the point G and A, the horizontal distance is 58. But here we consider the vertical distance, which is 24. And the reason is because the acceleration is in horizontal direction. I mean, in this system, this is the acceleration of the mass center. If you want to find the moment due to this acceleration about the mass center, what's the arm of this acceleration? The arm is this length, 24, okay? But if this system was moving in the y direction, and here you had, for example, AY in this direction, then if you wanted to substitute the D, then D was 58 because the motion was in y direction, and the arm of the acceleration about point A was this horizontal component, which is 58. But here the system is moving in x direction, and the moment due to the acceleration AX, its arm is 24. Now you can write the moment equation about point A, and we will have the force 3,600, which is the weight of the car times by cosine theta, which is the vertical component, times by its arm, which is 58. The weight horizontal components times by sine theta times by its arm, and 120 Newton times by NB, the reactions here at point B, and dy, which is calculated in previous part. Okay, and finally dx multiplied by this 18". Okay, so this is the moment about point A, and you can consider one direction for your force. Here, for example, we consider that the clockwise is positive. So this, the vertical component of the weight about the point A is positive, the horizontal is negative. The moment due to this NB, the normal reaction at B, is negative. The moment due to dy is positive, and the moment due to dx, which is this red vector, this one is again negative. So here it must be equal to, as I told you, m times by a times by d, and from this equation you can easily find NB. Okay, so this is the normal reaction at point B. If you need to find the normal reaction at point A, you can write the force equation in y direction, and you can easily find the normal reaction at this point, or this NA. Okay, any question? Is it clear? If you don't have any question, we can wrap up and this chapter, and we can start the next chapter. Of course, we only have about 8 minutes. We can just start the introduction of the next chapter. Any question from this example? No question? Okay. Okay, we continue the plane kinetics of rigid bodies. In this part, we will cover two important types of motion. One is fixed axis rotation, or the pure rotational motion, and the second one is the general plane motion. Okay, so we will have two different types for motion in this chapter, and we will discuss them. The fixed axis rotation, as I told you, is similar to pure rotation. In fact, in this type of motion, as you maybe know, the acceleration will be considered in two directions. As here you can see, here this is the tangential acceleration and the normal acceleration, normal component. We can assume that this system is moving with a pure rotational motion about point O, with angular acceleration alpha and angular velocity omega. The tangential acceleration is equal to r times by alpha, which r is the distance between the point and point O. So you can find the acceleration and velocity for each point on this body when you have a pure rotational motion. And the tangential one is equal to r alpha, and the normal one is equal to r omega squared. So in this case, you can easily find the motion, the velocity and the acceleration for each point on the rigid body. And all of the points have the same angular velocity and angular acceleration. So for this system, you can write the moment equation. For this system, you can write the moment equation. It's equal to mg is equal to I alpha. I bar is the mass moment of inertia about the mass center, and alpha is the angular acceleration. This term, this is the alpha. Or you can write the moment equation about point O, which point O here, this is the fixed point of rotation, and it must be equal to IO alpha, which IO is the mass moment of inertia about point O multiplied by alpha, which is the angular acceleration of the system. And IO, you know from the previous chapter, you know that IO is equal to I bar plus M R bar squared, which R bar is the distance between G and O. Okay, so you can write the moment equation in these two forms according to your problem. Usually using the second form will decrease your calculations. And this is the point. If you substitute instead of I-O, you substitute I bar plus M R bar squared, you can conclude that this moment equation about O is equal to I-O alpha. Here you can see in previous slide here, I told you when you are writing the moment equation about any other points than the mass center, in the right hand side here, you will have some addition terms plus M A D, okay? But here you can see that we neglect this term. Here we only have I times by alpha. And the reason is that when you have the pure rotational motion, if you write the IO, it's equal to I bar M R bar squared. And if you substitute here, you can see this term will be vanished. Let me change the color here. This term, which is M times by D squared times by alpha, because the acceleration for that point is equal to R times by alpha. You know that in this term we had M times by M times by D. A is the acceleration, which in this case, when we have pure rotational motion, is R times by alpha, and D is equal to R. So we will have M times by A times by D, which is this term, M R squared alpha, and it will be cancelled out with this term because I O is equal to I bar plus M R squared. So instead of I bar, if you substitute I O minus M R squared, you will cancel out these two terms, and in the right hand side we only have I about O times by alpha. So in fact this is the same equation, but it will be simplified because we have a pure rotational motion and the acceleration for each point is equal to R times by alpha. Okay, so this is the point that we are using this equation. Any question from this part? Because we only have 2 minutes, I think we should wrap up this session, because if I start this example, it will be interrupted by the Zoom, because as I told you, I'm using the personal version and I have time restriction and only I can use 40 minutes from this software. Okay, any questions so far? Is it clear? Okay, so we can continue this example tomorrow, and tomorrow we will have again 2 sessions. I will start at 4 p.m. till 4:40, and again we will have a 10 minutes break, and then I will continue again another session, another 40-minute session. Okay. Okay, thank you. No questions, so we can wrap up this session. Okay, thank you and have a good day.